You've seen the sun 1,000 times in photos, but have you ever seen the sun from above? Think about that for a second. Every image of the sun you've ever seen in the news, in school books, in eclipse photos, was taken from more or less the same place, from the side, from the edge. No one has ever looked at the sun from above, staring straight at its pole, like looking at a spinning top from above. And there is a direction now, right above you, where almost nothing humanity has ever launched into space has managed to go. It's not because of distance. The sun's pole is exactly the same distance from you as the rest of the sun. The problem isn't distance. The problem is up. And that's one of the strangest things about the place where we live. There's a direction right there, perpendicular to everything, that's harder to reach than the icy edge of the solar system. Today, we're going to understand why. Why the universe makes it easy to go sideways and almost impossible to go upwards. What's up there? At that angle, no one has properly photographed. And the strange maneuver, falling toward the sun and then being able to go up, which is finally starting to open that door. I'll start by debunking the first misconception, since it's one most people have. You probably think it's a matter of power, that we haven't gone above the sun because we don't have a rocket strong enough yet, that it's just a matter of time and a bigger engine. That's wrong. We've already sent probes outside the solar system. We've passed by Jupiter, Saturn, Pluto, and we're heading into the space between the stars. We have distance and power. What's missing is something else. And it's something that has to do with the way you, me, the Earth, and everything else are moving right now without feeling it. And maybe you think, so is it just a matter of priority, of budget, of NASA or Europe deciding to spend money on this? It's not quite like that either. It's not a lack of will, nor just about money. It's that there's a wall of physics in the way, a wall made of motion that no check, no matter how big, can knock down on its own. To understand what this wall is, you need to feel something that's happening to your body right this second, and that you've never noticed because you're moving right now. Not because of any earthquake, not because of any wind. The entire Earth is sweeping sideways through space, around the sun at about 30 kilometers per second. 30 kilometers per second. 30 kilometers per second. In the time it took you to hear this sentence, the planet has already carried you a few hundred kilometers sideways. You don't feel it because it's constant, it's smooth, and everything around you, the air, the ground, the oceans, your coffee, moves together at the same speed in the same direction. It's like being on a perfectly smooth train that never breaks. On one of those trains so smooth that you only notice the movement when you look out the window. And that's where the point that changes everything is. Any rocket that takes off from Earth is already born with that sideways speed. It doesn't start from a standstill. It starts with 30 kilometers per second of lateral movement around the sun for free just by being on the launch pad. To reach the edge of the solar system, the rocket just needs a little push in the direction it's already going, and the sun's gravity does the rest of the work. But to go up, to leave this plane and look at the sun from above, it would have to cancel almost all of that lateral speed and replace it with an equivalent speed pointing upward. And that, in terms of fuel, is brutally expensive. To understand why it is like this, and why it couldn't be any different, it's worth going back to something that Feynman explained with a simplicity that almost no one else achieves. There's a passage in the book Feynman's Tips on Physics in chapter 4 where he stops and asks something that seems obvious but is fundamental. He notes that all the planets revolve around the sun more or less in the same plane. Almost all of them revolve in the same direction. Most of the moons do as well. And he asks, why did the solar system end up like this? Why is everything so flat? So organized? So in agreement? Feynman's answer is angular momentum. Imagine a giant cloud of gas and dust, much larger than any solar system, slowly spinning in space. Gravity pulls everything inward, and when something that's spinning contracts, it has to spin faster. It's the same reason why a figure skater spins faster when she pulls her arms in. The arms of the cloud pull in and the rotation speeds up. But there's a beautiful detail here. The cloud is able to collapse freely from top to bottom along the axis around which it spins. What it can't do is collapse sideways because the rotation holds it. It pushes it outward. So the top and the bottom collapse. The sides resist. And what was once a ball of gas, after a long time, becomes a disk. A thin, spinning disk with the sun forming in the middle. The planets formed inside this disk, and they inherited its shape. Anything that tried to stay too far above or below the plane was pulled back, or flung far away, or simply never came together. The solar system is flat because gravity plus rotation almost always make a disk. Saturn's rings are a disk. The entire galaxy, the Milky Way, is a disk. Feynman was talking about our neighborhood, but he was describing a rule that repeats at every scale where gravity and rotation work together. A round solar system would be weird. Flat is what's expected. And here's something that might make you look at the sky differently the next dark night. This disk is not abstract. You can see it with the naked eye. On a very clear night, far from the city, right after sunset or just before dawn, you can see a pale, slanted cone of light rising from the horizon, following the same line where the sun and the planets pass. It's called zodiacal light. It's not the glow of the atmosphere. It's not an aurora. It's the sunlight hitting the fine dust that still lines the plane of the solar system today and coming back to your eyes. When you look at that band of light, you're literally seeing the geometry of your home, the disk in which everything revolves, seen from the inside, edge on. The line that the sun, the moon, and the planets travel across in the sky even has a name: the ecliptic. You may have traced it with your eyes without even knowing it, by noticing that Venus, Jupiter, and the moon always appear more or less along the same curve. They follow this line because they follow the same plane, because they were born in the same disk. And this is where it gets beautifully uncomfortable. This disk isn't just a detail from a schoolbook illustration. This disk is a current, and you're inside it. Think of a wide, calm river carrying everything in just one direction. A leaf falling into water drifts down the river effortlessly. The current carries it. Going with the flow is easy. Now try to swim straight across that river, perpendicular to the current. Suddenly, all the water that was helping you is now working against you. The solar system is exactly like that. Going sideways with the flow toward Jupiter, Saturn, Pluto is like going down the river. Going up perpendicular to the plane toward the sun's pole is like crossing the entire current at once. The leaf isn't stuck, but getting out of the river costs much more than staying in it. Engineers have a name for the money a probe has to spend on changes in movement. It's called delta V, the change in velocity it can produce with the fuel it carries. Each maneuver costs a certain amount of delta V, and when it's gone, it's gone. It's the currency of the solar system. And the numbers tell a story that almost sounds like a cosmic joke. It's worth examining the numbers. They have a beautiful logic. Leaving the surface of the Earth and reaching low Earth orbit costs around 9 to 10 kilometers of delta V, which is the most expensive part of almost any mission. You use it fighting gravity and air at liftoff. Leaving Earth's orbit towards the moon costs another 3 or 4 kilometers per second. Going to Mars on the most economical trajectory and with the planets well aligned costs about 4 kilometers beyond Earth's orbit. To Jupiter, about 6.5 kilometers. All of these are destinations within reach of today's rockets because they're all inside the disk, and going sideways is like going downstream. Sending a probe straight up, perpendicular to the plane, to a height that's not even that great, costs about 30 kilometers per second of delta V, more than any chemical rocket has ever delivered to a single spacecraft in history. The largest interplanetary missions ever flown have carried in their entire lifetime something between 15 and 20 kilometers per second in total. A straight ascent is not just slightly out of reach, it's completely out of reach. Feel the weight of that for a moment. Getting to Pluto, out there on the frozen edge of everything, is cheaper than going straight up to the height of Earth's own orbit. The empty sky, just above the sun, is, in practical terms of spaceflight, more remote than the most distant planets. Not because it's far, but because getting there means escaping the plane that gravity locked us into 4.5 billion years ago. The current rewards those who go with it and punishes those who resist. But there's a trick. It's one of the most elegant tricks in space engineering. Instead of fighting against the planet's gravity, you use its gravity. A probe skims past a planet, and that planet's gravity redirects it. It gives or takes away speed. It changes direction without burning much fuel. The planet, being immensely larger, loses such a tiny fraction of its own speed that no one will ever notice. The energy is conserved. The probe borrows just a little bit of the planet's movement. It's called gravitational assist, and it's the closest physics gets to a free lunch. Jupiter. The most massive planet is the biggest natural slingshot there is. A single flyby near Jupiter can change a probe's speed by about 10 km/s. And with the right angle, Jupiter can throw a probe out of the plane of the planets, sending it upward. There's an even more counterintuitive second trick. It's key to this story's future. To go up, sometimes the best thing to do is to fall first, to fall toward the sun. It works like this. The deeper you are in a gravitational well, the faster you move. A probe that lets itself fall toward the sun is accelerated by its gravity to enormous speeds, well over 100 km/s at the closest point. And that's where the magic comes in. The engine, which fires when the probe is already moving very fast, extracts much more energy from the same fuel than if it fired with the probe moving slowly. The push generates energy that increases with the square of speed. The same kilogram of fuel, the same flame, but if you burn it at the bottom of the well, when you're already flying, the effect is disproportionately greater. This principle was formalized in the early days of rocket science, and it's the same principle that every probe uses when it fires its engine at the closest point to the planet, where it's moving fastest. Apply this to the sun, which is the deepest well in the solar system, and you have one of the most beautiful maneuvers ever imagined. The probe falls toward the sun, gains tremendous speed, and then, at the closest point, fires its engine for just a few minutes. Because of the deep well effect, that short push results in a gigantic change in orbit and, with the right direction, throws the probe out of the plane, toward the sun's pole, for a fraction of the cost that a straight ascent would require. The 30 km/s of DV, which seemed impossible, become maybe 3 or 4 applied at just the right moment. The only price is surviving the heat near the sun. It's difficult, but engineering has proven it's possible. And there's even a third way, perhaps the most poetic of all, that doesn't burn any fuel: the solar sail. Sunlight has no weight, but it does have a push. Each particle of light that hits a surface and reflects gives a tiny bit of momentum. By itself, this push is too small to notice, but spread an ultra-thin sail, thinner than a plastic bag, over thousands of square meters, and let sunlight hit it for months, years, and the combined push turns into real movement. A sail spacecraft can tilt its own sail like a sailboat angles its sail to the wind and gradually climb out of the plane without spending a drop of propellant. It's slow. It trades time for fuel, but it doesn't run out. As long as the sun shines, the sail has thrust. The most promising proposals combine both ideas. A sail gently takes the ship close to the sun, and there, at the bottom of the well, a small engine gives the decisive push that throws it out of the plane. None of these missions have been built yet. They exist on paper, calculated, tested in parts, waiting. Leave the blackboard behind and see what has flown. Because in the entire history of humanity, only 2 machines have actually managed to go up and look at the sun's poles. 2. And both stories are incomplete in a way that says a lot about how tough this problem is. The first one was called Ulysses. It was a joint mission between the European Space Agency and the American one, and the name came from the Greek hero who wanted to sail beyond the known world. It was launched on October 6, 1990 aboard the Space Shuttle Discovery, and its trajectory is one of the smartest ideas in space engineering. Ulysses didn't go toward the sun. It went in the opposite direction, outward toward Jupiter. On February 8, 1992, it passed by Jupiter and used the giant's gravity to fling itself out of the plane of the planets, tilting its orbit by more than 80 degrees relative to the ecliptic, almost perpendicular to everything. It was the first object in history to truly leave the plane of the solar system to fly over the sun's poles. And just so you have an idea of what it took to get it off the ground. When it left Earth, Ulysses was going at about 15 kilometers per second, the highest speed ever reached by a human-made object up to that point. Faster than the Voyagers, faster than the Pioneers. Even so, on its own, it would never be able to achieve the inclination it wanted. It was the gravity of Jupiter, and only it, that bent the trajectory out of the plane for free. The almost 2.5-year detour to Jupiter was longer than a straight ascent would have been. The direct ascent was impossible, but the detour was not. It was the first practical proof that it was possible to reach the sun's poles, as long as the mission was smart enough with another body's gravity. Ulysses confirmed for the first time, by measuring on the spot, something that until then was only theory, that the fast solar wind really does come from the poles. And it's worth pausing here, because this is one of the most beautiful discoveries it brought. The sun gives off two kinds of solar wind. From the poles, fast wind gushes out at about 750 to 800 kilometers per second, almost twice the speed of the wind that comes from the regions around the equator. From the sun, which drags more slowly, between 300 and 500 kilometers per second. Ulysses flew through both regions and measured the two winds exactly where the models predicted. The fast wind arrived from the poles just as predicted. For the first time, someone had gone up there to check. She brought more. She measured how the sun's magnetic field spirals outward through the entire solar system, forming a giant, wavy surface. A kind of ballerina skirt that rises and falls as the sun rotates, and whose tilt changes throughout the 11-year cycle. As Ulysses climbed to higher latitudes, it crossed this skirt less and less, just as you would expect from a structure concentrated near the sun's equator. And in a detail that almost no one expected, the Gordo dust detector recorded dust grains coming from outside the solar system. Real interstellar dust blowing in from the space between the stars, measured there, far from the plane where it had never been measured before. But there's one thing Ulysses couldn't do. It didn't have a camera. None of the instruments on board was capable of photographing the surface of the sun. It was a flying physics laboratory, sensing the magnetic field, counting particles, measuring the wind, but blind to the image. It spent almost 2 decades in that inclined orbit, ended operations in 2009, and to this day it keeps circling, silent, above and below the sun. It measured everything. It didn't photograph anything. After it went silent, the face of the sun's poles, the real appearance of that surface seen from above, remained practically unknown. And this is where the second machine comes in, and it's recent. So recent, that part of this story happened just a few months ago. It's called Solar Orbiter, also a mission of the European Space Agency with NASA, launched on February 10, 2020. Its strategy is different from Ulysses. Instead of a single giant swing by Jupiter, the Solar Orbiter uses repeated flybys of Venus, each one tilting its orbit a little more, slowly, over the course of years. It's patient. Each visit to Venus bends the orbit a little more upward. And unlike Ulysses, the Solar Orbiter carries real cameras, a whole set of instruments made to see. There's a telescope that sees the surface of the sun in visible light and maps the magnetic field point by point. And there are ultraviolet cameras to capture the structure of the corona, the sun's outer atmosphere. There are instruments that measure the solar wind right there around the spacecraft. It's a flying solar observatory. Where Ulysses could feel but not see, the Solar Orbiter can feel and see at the same time. The missions complement each other. One proved that the poles are different. The other is showing what they look like. In February 2025, a flyby of Venus tilted the probe's orbit from about 7 degrees to 17 degrees relative to the sun's equator. It doesn't seem like much, but it was enough. On March the 16 and 23, 2025, the solar orbiter took the first direct images of the sun's south pole ever obtained in history. For the first time, human eyes saw the sun from that direction with real resolution. And what appeared didn't look like the equator. The surface there was thinner, more tangled. The magnetic field, instead of a clean pattern, was a mess of mixed polarities. North and south together in the same place. It was a part of the sun that no one had ever been able to look at directly. And the best part is that this is just the beginning. The mission team itself calls it the stairway to heaven. The probe will keep tilting its orbit, reaching 24 degrees by the end of 2026 and 33 degrees in 2029. With each step, a better view. After an entire history of solar physics spent looking at the sun from the side, we finally started to climb. Why is seeing the poles so important? Why isn't looking at the easier equator enough? Because the poles are not just any region of the sun. Because they are the engine room. That's where the fast wind is born. That's where the sun's magnetic field reverses. Because about every 11 hours, the sun switches its magnetic poles. What was north becomes south, and south becomes north. This 11-year cycle controls almost everything we see on the surface. The number of sunspots, the frequency of eruptions, the size of active regions, and the reversal starts at the poles. The new magnetic field builds up in the polar regions over the years until it flips the switch for the entire planet. The strength of the polar field at the end of the cycle even determines how intense the next cycle will be. Whoever understands the poles understands the engine. Whoever only looks at the equator is studying the symptoms and missing the cause. And this magnetic memory of the sun holds long stories. Not every 11-year cycle has the same strength. There are centuries-long periods when the sun becomes noticeably quieter, with few sunspots. And these long silences seem to be linked to weaknesses in the polar field that drag on for several cycles. There's also a detail that helps turn this engine. The sun doesn't rotate like a solid ball. Its equator makes a full rotation in about 25 days, but near the poles, the rotation takes more than 30 days. This difference twists the magnetic field lines over the years, winding up the structure that later produces sunspots, eruptions, and eventually the reversal of the poles. It's a clock that winds itself, and the hands live where we almost never look. Think about that. The sun that warms your skin, that makes your food grow, has a magnetic heart that pulses in a region no human eye had seen head-on until a few months ago. And there's an image of the poles that's worth keeping. From the polar coronal holes, the dark and open regions where the fast wind escapes, long thin jets of plasma come out, called plumes, aligned with the magnetic field lines, like blades of grass pointing outward. Seen from the side, they look like faint rays curving away from the sun. But imagine seeing this from above, right over the pole. What was once a ball of fire would turn into a kind of eye, a quiet and granular surface, crossed by plumes spreading outward in all directions, like the petals of a flower spinning very slowly. Less like a star, more like the open eye of something patient and very old. That's the kind of view no picture from the equator can give, and that we've only just begun to glimpse now. And it's not just the sun that would look different from above. The whole sky would change. Our galaxy, the Milky Way, is also a disk, but it's a vastly larger disk, and it's not aligned with the disk of the planets. The two planes are tilted relative to each other by about 60 degrees. Seen from Earth, the Milky Way stretches horizontally across the night sky. From above the sun's pole, this band would tilt sharply, and the brightness of the center of the galaxy would appear in a different direction than we are used to. The same stars, the same sky, but rearranged in a way that would seem strange even to someone who spent their whole life looking up. We live at the meeting point of several disks. The planet's disk, the galaxy's disk, each with its own tilt. Each one is a memory of an ancient rotation that flattened everything. And we've always looked at all of them from inside just one. And the sun doesn't end where the planets end. The solar wind keeps blowing outward, getting thinner and thinner, carrying the sun's magnetic field for an immense distance until it hits the gas between the stars. Where the pressure of the wind and the pressure of the interstellar gas balance each other, a boundary is formed. And the giant bubble of solar plasma inside this boundary is the heliosphere. Everything you know as the solar system lives inside this bubble. It's our shield, our local climate, the limit of the sun's influence. Here's something else that will bother you a little. We don't know the shape of this bubble. For decades, the standard drawing was that of a comet, a rounded head in the front where the sun pushes the gas it encounters, and a long tail behind. But more recent measurements have suggested a very different shape, more like a squashed croissant, two lobes curving backward with no long tail. We have two witnesses to this boundary, and both have the same limitation. The Voyager probes, launched almost half a century ago, crossed the edge of the heliosphere and entered interstellar space. Voyager 1 in 2012 and Voyager 2 in 2012. These are the most direct measurements that exist of the edge of the bubble. But both cross the boundary more or less at the front, in the direction the sun is moving, and more or less within the plane. They couldn't see the tail. They couldn't see the shape from above or below. They could only measure the part of the bubble in their path. A third probe called IBEX did something ingenious. Instead of traveling to the border, it mapped the bubble from afar, detecting neutral atoms that come back from the edge toward the sun. And it discovered an unexpected bright band crossing the sky, an emission ribbon whose origin is still being unraveled. All these clues, however, come from within. Why don't we know the bubble's correct shape? For the same reason as everything tonight. Because every measurement we've made of the heliosphere was done from within the plane of the planets. No one has ever seen our bubble from outside or photographed it from above. The solar system has been mapped planet by planet over centuries. But the outline of our home, the line that separates the sun's reach from the rest of the galaxy, has never truly been drawn. Now imagine, just for a moment, that one of these probes finally managed to stop above the sun's pole. What would it see? The first thing would be that the sky would become clearer. From inside the plane, the whole sky has a faint glow. Sunlight scattered by the dust that accumulates along the ecliptic. The same dust that, on a very dark night, you can see as a pale cone of light just after sunset. This glow makes it hard for those trying to see very faint and distant things. From above the plane, this glow is left behind. The sky up there would be darker, clearer, and emptier than any view possible from inside the solar system. Telescopes searching for signs of life on other planets around other stars, or measuring the oldest light in the universe, would get one of the cleanest windows there is. That's not just technical. Consider what that means. One of the biggest obstacles to seeing the atmosphere of a distant planet, to look for the same gases there that life leaves in Earth's air, is precisely this dust in our own backyard, scattering light and interfering with the faint signal that comes from far away. From above the plane, much of this nuisance disappears. The same advantage applies to the background light of the universe, that faint glow left over from the very first moments after the beginning of everything, which carries the oldest story there is. Measuring this glow precisely is one of the most difficult things in astronomy, and the dust in the solar system gets in the way. Above the sun's pole, the signal would be clearer. I mean, the same place where we would finally see our own home in its entirety would also be one of the best windows ever found to look at the rest of the universe. The direction we've ignored the most is also the clearest one. And then the probe could turn its instruments downward, and it would see for the first time in history the entire solar system's disk from above. The orbits of the planets, which today are known only by calculation and inference, would appear all at once in a single glance. The Earth and the inner planets as bright little dots gliding along their paths. The asteroid belt as a thin band between Mars and Jupiter. Everything laid out on a great sheet below the ship, illuminated by the sun behind. It would be the first portrait of the solar system as a single object seen from above. This photo doesn't exist, has never been taken, and can't be taken from anywhere within the plane, because the plane's very geometry forbids it. And if that same probe had the stamina to keep going up year after year, it could finally settle the debate about the shape of the bubble. Measuring the magnetic field in plasma at various latitudes and distances would distinguish between the comet-shaped and croissant-shaped models, since both predict different outcomes there. And if one day it crossed the boundary of the heliosphere from above or below, far from the nose, it would bring the first measurement of the edge of our home from a direction no one has ever shown. It would be for the outline of the solar system what the Voyagers were for its front. One way or another, the portrait of our home would finally gain an outer line drawn by observation, not by guesswork. I confess that after diving into this story, I started looking up in a different way. Not at the night sky, we always look at that, but at the direction perpendicular to everything that's right above my head while I walk around without thinking. I started to feel that there's a window right there, close by, that's been open for 4 billion years, and we've almost never turned to look at it. Not because it's far, but because it's to the side. And maybe that's what makes this whole story so beautiful. We often think what we have yet to discover is always far away, deep in space in another galaxy on some unreachable border. But the view that's most missing from our family album isn't far away. It's right above the sun that rises every day at your window. The engineering exists and the trajectories have already been calculated. We just haven't flown yet. The sun keeps turning slowly in the quiet center of the disk, as it always has. The planets follow their orbits. The swift wind gushes from the poles, as it always has. No one needs to watch from the right direction for this. The processes don't need the photograph. The photograph is for us. The plane around us continues, and the photo that is still missing is not a loss. It's a promise, waiting with the patience of someone who has already waited billions of years for the only direction we still haven't had the courage to turn to.